Welcome. In this video I'll introduce the cold plasma dispersion relation, and this is a way of looking at how the plasma responds to waves. This could be light waves, or it will look at different waves like Whistler waves or Langmuir waves, and this is looking at how the plasma responds to fast fluctuations. And so we're going to look at how what the conductivity of the plasma is. So if you impose an electric field, how does the current in the plasma move? How does the plasma respond to external magnetic and electric fields? This gives rise to an expression for the refractive index, which tells us how waves move through the plasma, where they're reflected and where they're absorbed. And then we'll start to look at particular kinds of waves that we get in plasmas. And so this whole process starts by looking at that Maxwell's equations. So we'll start by using these. So note that here we've used the displacement current. So most of the lectures so far we've neglected this because it's usually small. We're usually looking at very slow frequencies, and so this can usually be neglected. Here we're looking at frequencies which can become large, and so we need to keep this, and this eventually will become a light wave. So if the current goes to zero, this becomes a light wave in vacuum. Okay, then we're going to look at plane wave solutions. So we're going to look at solutions where we have all quantities varying, like e to the I kx minus omega t. And this means that we can simplify all derivatives. We can just replace with ik, and all time derivatives we can replace with minus I omega. And this will simplify all these equations and also the plasma equations that we'll use shortly. So if we go, I'll try and keep this on the screen. So if we just do this substitution here, and we replace in these gradients with k's, and these d by dt's with omegas. So then we get these expressions here. So here I've just replaced the i's and divided through by i's. We get this minus I here from dividing 1 here by I. And then here we have a d by dt is just turned into an omega. And then these we can substitute in. So we just take this b here and we substitute it into that expression there. So we have a k cross e. So we have here is k, so this k here, crossed with, and now we have a k cross e divided by omega. And we can multiply through by omega, so the right hand side will become, so we have an omega factor here, so we have minus I omega, because I've taken this omega from k cross e and multiplied through. We have mu naught j. Now we have an omega squared, c squared times e. Okay, now in vacuum, I said the current here goes to zero, and so everything about the plasma goes into this J. So this contains the plasma response. And so in vacuum we just have this k cross e, and here I have omega squared over c squared. And this of course just gives light waves with speed c. This part here we can rewrite, and then there are several ways of writing this, but one is essentially to linearize the plasma equations. And so we write that the current in the plasma is some linear relationship between the current and the electric field, and the most general relationship we can have is a tensor. So we just write that the current vector is a tensor dotted with the electric field. And so this could be any large matrix, so essentially a 3 by 3 matrix relating the electric field in each direction, x, y, and z, to the current in x, y, and z. And so sigma here is a conductivity tensor. And this allows us to write this dispersion relation here as, so you have a k. You have a k dot e, so here this just ends up with a k, and minus this k squared e. Then this factor here also has just an e. I'm moving it from the right side of the equation to the left, so it becomes a plus. So I omega mu naught, and then a sigma for this conductivity tensor, and then plus omega squared over c squared from this last term here. And all these terms are dotted with the electric field. And so what we have here is this is a big matrix, so a 3x3 matrix, which depends on space in general, but here it's a 3x3 matrix dotted with the electric field is equal to 0. So this is a tensor, so a 3x3 matrix. And if the so this has several solutions. If this matrix can be inverted, then the solution is just that the electric field is 0. And so in order to have a non-trivial solution, in order for there to be a wave, the determinant of this matrix must be 0. Because only if the determinant is 0 can then this can't be inverted, and so we can't move this to the right side and just get E equals 0. So that's a condition for having a wave. So this is generic, only depends on Maxwell's equations. The plasma physics part comes into this sigma. And so now there are several models we can use to work out a sigma and then work out the waves from that. And so what we're going to do now is the cold plasma. So we're going to assume a cold plasma response, and so work out if T, so all the pressures, so P electron pressure and ion pressure are equal to 0. And so the only equations we need to solve are the momentum equations for the ions and electrons. And so these we can just write down with no pressure terms. So we have the ion mass times N, and the change in the ion flow velocity. And this is just J cross B. We can assume small fluctuations in B, so just have the perturbed J. This is a vector U, so that's for the ions. And then for the electrons, you just have Ohm's law. So again with no pressure term. So here we have E plus U, the ion flow. And then here we have the other terms that we've talked about previously. So we have a J cross B naught. So the Hall terms, there's no pressure term. Then we have the electron mass term. So I'm simplifying a little bit to just keep this term. Okay, so we're going to solve these two equations to work out what the current is and how the current depends on the electric field. So the electric field is coming from this wave, and then we need an expression for this conductivity, which relates the currents to the electric fields. So we do the same thing as before. We assume solutions like e to the I k dot x minus omega t, and make the same substitutions as we did earlier for Maxwell's equations. And so this then gives, and then we substitute the ion equation, this ui, into here. And so we again eliminating these flow velocities, the ion flow, and just trying to get an equation in terms of just currents and electric fields. And so we can simplify this a little bit. Where here I've just taken this U and substituted into here, and so this is just rearranging this ion flow and putting it into this expression here. And now we can start to simplify some of these things. So I'll get different color. So this one, for example, this is just the perturbed, so the current in the perpendicular to the magnetic field times B naught squared. This term here we can simplify, and this is going to be essentially depends on the plasma frequency. And so this we write as 1 over pi. You're going to call capital pi E as the plasma frequency, so electron plasma frequency, times epsilon naught, where pi E is so that should be pi E squared. So we have n E squared over me, and here we have an epsilon naught, so we have an epsilon naught in there. Now this term over here, so we're going to try and get pi E squared from all of these terms. So any density here is going to turn into a pi E. and so this density here we turn into pi e, and so we end up with 1 over pi e squared. Here we have still an omega. We have an m e from this. Have an mi. We end up with an e squared term again from the pi, and an epsilon naught as well. And then these e squareds, b squareds, and the different masses. So these will turn into the cyclotron frequencies. So these terms combined with these terms to give us like an omega e, so the electron cyclotron frequency times the ion cyclotron frequency. So here I have omega e is just e times magnetic field over electron mass, and omega I is just e, the same thing but with the ion mass. This is mi. Okay, so putting all these terms together, we can simplify. Again, the same thing here, that density will turn into a pi e squared, and so I'm going to write out this. So this first term here with the omega e, omega I has come from this j cos b term. This second term here has come from this whole term here, where this little b is just the unit vector, because you use this magnitude of b to turn into an electron cyclotron frequency. And then we've multiplied through by omega everywhere, and so this omega becomes an omega squared, and we have an omega squared j. And so now we have an expression which has the electric field on the left and essentially current on the right hand side. So this is essentially what we're looking for. This is a conductivity tensor, rearranged slightly. So this is so to actually write down what this tensor looks like, we need to pick a coordinate system. We need to pick a basis of some kind, and so we need to pick a direction. And so what we're going to do is we're going to choose basically a z direction is along b. So that b is just bz, and then we can choose k. So we can choose an x direction, which is along the k perpendicular, and so we can choose k. Basically has a component which is along z, so along b, and a component which is perpendicular to z. I'm just going to call that direction x. And so this is still general. We've just chosen a particular direction, and so we're just going to say that k is kx, 0 kz, so the ky component is 0, and that's just because we've chosen our x direction to be in the direction of k. And we can also label this as k perpendicular. So this is the component which is perpendicular to b, and k parallel is the parallel component to b. And lastly, we can also write this as a k sine theta and a k cos theta, where theta is the angle between. So here we have so you have b, which is in the z, and we have some k vector, and this is this angle theta. So if you have k along b, then this k perpendicular goes to 0, and if theta goes to 90, then this goes to 0, and we just have k perpendicular. Okay, using this basis, we can then write down an expression for what the electric field looks like by essentially putting this expression for k and b into this plasma response expression, and combining that with this expression from Maxwell's equations. So combining it with this expression here, as you see, it's quite a long process, but it's fairly straightforward, and you end up with a matrix. So it's a 3x3 matrix for each of the components of E, and as I said before, if E is not 0, then the determinant of this matrix should be 0 in order to have wave solutions. Now I should explain several quantities in here. So here we have n, is capital N. This is the refractive index. So n is a refractive index, which is c times k over omega. And so here, for example, n parallel is just ck parallel over omega, and n perpendicular is just ck perpendicular over omega. So this is a refractive index, so it tells us how the wave moves, how it either refracts, so it deflects from a straight line. It also tells us when it's absorbed. And so, for example, if you have n squared is bigger than 0, then it's propagating, so it's an oscillating wave. And that's the standard case, so a light wave in vacuum has n squared equals 1, so all bigger than 0. So if we have n squared is less than 0, what this means is that we have an imaginary imaginary k or imaginary omega, and this means that we have a decaying wave. And so this is something called evanescent wave. And the point where n goes from positive to negative, so where n squared goes to 0, this is where a wave will typically reflect. So if this ever happens, then the waves will tend to bounce back, and then past the point where they've bounced, there'll be a small decaying evanescent wave. What can also happen is that the wave can be absorbed. This happens so if n squared goes to infinity, then so this omega goes to 0, then we have resonance and absorption. So for example, if a wave has the same frequency and the same handedness as an oscillation, say, of a charged particle like an electron, then it can resonate with that motion and then be absorbed by the plasma. And in that case, n squared goes to infinity. And so this is what we want to find out, is how the wave's propagating, if it's absorbed or reflected. And this is these n factors in here. These s, d, and p factors. S and d stand for sum and difference, and it's a right and left-handed waves. So whether as you look down the magnetic field, if the wave is twisting to the right or twisting to the left as it propagates. And so write down what these are. So here's S and D, so is the sum and difference of these R and L factors. So R stands for right-handed, and L stands for left-handed. And these are essentially waves which have absorption either in the right-handed sense or the left. So say if you're looking down a magnetic field and you're looking at the electric field vector of the wave, as it propagates, the wave is either twisting to the right or twisting to the left, and this corresponds to these R and L's. Note here that this is negative, so omega E is less than 0. I think I may have missed out a sign up here. Oh yes, so this has a minus sign in it, so here omega E is less than 0. And so the right-hand waves tend to resonate with the electrons, and the left-hand waves resonate with the ions. Now the only factor I'm missing here is the P. So here those are the S and D's. These are all refractive indices, and then P is this last one. So P, this just corresponds to the plasma frequency. So this is approximately 1 minus pi E squared over omega squared, and this is the plasma frequency. So there are many different solutions to these equations. Particularly interesting are there's the parallel components and the perpendicular waves. So if you look at perpendicular waves, for example, you get O mode and X mode waves. These are relevant for things like plasma heating. We're going to look at here as parallel waves. So essentially where K is parallel to B. I.e. so Kx, K perpendicular, which here is Kx, is equal to 0, which of course means that also N perpendicular is equal to 0. And so this can simplify some of this parts here. So So n squared becomes n parallel squareds, n perpendicular goes to 0. So these components up here go to 0. And write down, and so we just take the determinant of this matrix here, and we end up with, which you can rearrange, just take this factor of p outside, and so we just write down that we have either, so s minus n all squared from here, here from d squared, 0. And so either p equals 0 is one solution, where p here is just the plasma frequency, and so if this is 0, then omega squared is just equal to pi e squared, so the plasma frequency. So this is omega squared is pi e squared. This one is called a Langmuir wave. So if so there's no k, it doesn't propagate, has no so omega doesn't depend on k, so there's no group velocity. So group velocity is equal to 0. If there's a finite plasma temperature, then this can propagate, but at 0 temperature, then there's no group velocity. So the other way that this can be 0 is if we have this part equals 0. So or we have so s. So this is the other way that we can make this determinant equal to 0, and we can write this out in terms of r and l waves. And so what we get is, and the solution to this is basically that n squared is either r or n squared is equal to l. And these correspond to the right-handed and left-handed waves. And so this right-handed wave resonates with the electrons, and the left-handed resonates with the ions. And these are also called Whistler waves, which we'll look at next in the next video.